Howdy. This video is on periodic trends in size, ionization energy, electron affinity, and electronegativity. The periodic table is the most powerful tool for predicting how elements behave. The periodic trends illustrate how characteristics of elements vary as one moves across the periodic table. The periodic trends enable us to predict which elements are larger, which are more likely to lose or gain electrons, and actually we can relate this to reactivity of the different elements. After watching this video, you should be able to describe how the electrostatic interaction between the outer electrons and nucleus varies as moving across the periodic table. Now we'll see that the electrostatic interaction between the outer electrons and nucleus actually determines the size, ionization energy, electron affinity, and is related to electronegativity. And so it's very important that you understand that this is all about the electrostatic interaction. You should be able to put the list of elements in order of increasing size, ionization energy, electron affinity, and electronegativity. You should be able to describe how an atom gets smaller when an electron is removed and gets bigger when an electron is added. So a positive ion is always smaller than the corresponding atom it came from, and a negative ion is always larger than the corresponding atom it came from. You should be able to put a list of ions in order of increasing size, ionization energy, electron affinity, and electronegativity. And so the energy of orbitals is actually determined by the electrostatic interaction. And electrostatic interaction is the interaction between charged particles. And so opposite charged particles attract, like charged particles repel. The larger the charge, the stronger the interaction. The shorter the distance, the closer the particles, the stronger the interaction. This is just Coulomb's law. And so the energy of electron orbitals is dominated by the electrostatic interaction. And so we've seen that the smaller the n is the principal quantum number. It denotes the shell and basically the size of the orbital. The smaller the n, the closer the electron is to the nucleus, the stronger electrostatic attraction between electron and nucleus. The larger the effective nuclear charge, the stronger attraction. And the effective nuclear charge is affected by the number of protons in the nucleus and the amount of shielding. The less shielding, the stronger the effective nuclear charge. Stronger attraction, lower the potential energy of the orbital, the more stable the orbital. And so each element has a unique set of atomic energy levels. That's because each element has a unique set of number of electrons and a number of protons. That's kind of interesting. If you notice, the 1s orbital keeps getting lower and lower as we add more protons in the nucleus, because the nuclear charge, the stronger attraction with electrostatic interaction, and that 1s orbital. The 1s orbital is always the lowest energy orbital because it's closest to the nucleus, has the smallest n. And so the electrostatic interaction dominates the energy of electron orbitals. We'll also see that it affects the size of atoms and ions, ionization energy, electron affinity, and electronegativity. And so if we think about the periodic table and we think about going down the rows of the periodic table, and we think about the quantum model of the atom, as you go down the periodic table, electrons are going into bigger shells. Their orbitals have larger n and larger size. And so as you go down, the atoms actually get bigger. Now as you go from left to right, you're adding protons to a nucleus, and so you're increasing the electrostatic interaction between outer electrons and nucleus, and so the atoms actually get smaller. And so if we add these two contributions as we go up and to the right, atoms get smaller. Now this periodic table is colored based on the size, and also notice that below the symbol is the covalent radius. There's actually a couple different ways of defining the size of the atom. I'm going to use the covalent radius. And so notice for fluorine, the covalent radius is 0.57. For francium, which is down on the lower left, is 2.6 angstroms. And so as you go up and to the right, atoms tend to get smaller. Now we call these trends because we will find exceptions, but in general, elements follow these behaviors. And so the size is due to electrostatic interaction between the outer electrons and the nucleus. And so that increases as you go up and to the right. And so the size decreases as you go up and to the right. Now we can also look at ions. And so if we take lithium and remove an electron, we form a lithium plus ion. And because we've moved an electron, we've reduced the amount of shielding between the electrons and nucleus. And so the positive ion is always smaller than the corresponding atom it came from. And so again, the positive ion is always smaller than the atom it came from because we've reduced the amount of shielding. Now if we take fluorine and we add an electron forming a fluoride ion with a -1 charge, we've increased the amount of shielding, The electron still goes into 2p, but we've increased the amount of shielding, and so the negative ion is always larger than the positive ion. And so again, this is always true. Negative ions are always larger than the atom it came from. Positive ions, cations, are always smaller than the atoms from which they were formed. Now, a question you could see would be, put the following in order, increasing size. And again, it's just about the electrostatic interaction. And we know from the periodic trends that as we go up to the right, we're increasing the strength of electrostatic interaction between the outer electrons and the nucleus. And so fluorine should be the smallest. Barium, which is on the lower left, should be the largest. And magnesium should be in the middle. And so again, size is about electrostatic interaction. And we know how that varies going across the periodic table. And so we can actually figure this one out. Now, you could also be asked the same question about ions. Now, for the size of the ions, it's still about electrostatic interaction, but because they're charged species, we can no longer use the periodic trends. And so we're going to have to figure out the strength of electrostatic interaction not using the periodic table. And so what we could do is we could look at the number of protons and the number of electrons. And so the number of protons is equal to the atomic number, which is given on the periodic table. And then for the number of electrons, well, oxygen has a 2-, so it has 2 more electrons than protons, and so it must have 10 electrons. Magnesium, 2+, and so it has a +2 charge, so it must have 2 less electrons than protons, and so it must have 10 electrons. And so all 5 of these species have the same number of electrons, same electron configuration, and so we call them isoelectronic. And so the one with the strongest electrostatic interaction between outer electrons and nucleus should be the smallest. And so magnesium +2 has the most protons, and so it should have the strongest electrostatic attraction between outer electrons and nucleus, and so it should be the smallest. Oxygen 2- has the fewest number of protons, and so it should have the weakest interaction between the outer electrons and the nucleus. And so we've seen size for atoms and size for ions. Now, ionization energy is also dominated by electrostatic interaction between outermost electrons and the nucleus. The ionization energy is the energy required to remove an electron from an atom or ion in the gas phase. And ionization energies are always positive because it's always going to take energy to remove that electron. And so we can imagine here we have the electron configuration for magnesium. And you can imagine that there's an energy state for electron by itself way up high. And so if we want to remove an electron, we're going to have to promote it to that much higher energy state. And in case of magnesium, it's going to take 738 kilojoules per mole. Now, once we remove one electron, we've reduced the amount of shielding that the other electron in the 3s orbital takes. And so less shielding have a stronger attraction with the nucleus. And so once we remove one electron, it's going to take more energy to remove the second electron. And so it always takes more energy to remove subsequent electrons. Now, the I1 means ionization energy for that first electron. I2 is ionization energy for that second electron. And again, I2 is always greater than I1 because of shielding. Now, if we want to remove that third electron, the third electron is in the 2p subshell. It's going to take even more because we're going down a shell. And so in the case of magnesium, it would be 7,733 kilojoules per mole. Now, because that's so large an energy, magnesium very, very rarely would form a +3 ion. And so magnesium typically forms a +2 ion.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and a greater effective nuclear charge. Thus, each successive ionization requires more energy. This graph shows the way in which the ionization energies of the aluminum atom increase as successive electrons are removed. Notice that the ionization energy increases with each successive removal of an electron. However, there is an especially large jump in the energy required for removal of the fourth electron. From a knowledge of the electron configuration of neutral aluminum, can you account for this dramatic jump?
And so the way I think about for aluminum, when you remove that first electron, it's in the 3p. The next two would be in the 3s. And then to remove that fourth one, you'd have to go down to the 2p. And so that's a lower energy, lower shell, and so it would take a lot more energy. And so aluminum typically forms a +3 ion. Now here's a table of ionization energies. Again, I1 is the energy required to remove the first electron. I2 is the energy required to remove the second electron. And so if beryllium forms a +2 ion, then it takes 900 to remove the first, 1,757 to remove the second. And so to go from beryllium to a beryllium +2 would take 2,657 kilojoules per mole. Obviously, only the first ionization energy is listed for hydrogen because it only has one electron. Going from left to right across the periodic table, generally the first ionization energy increases. Nitrogen is an exception because of the half-filled subshell, which is a little bit extra stable. I1 is always less than I2, is always less than I3, etc. And so we see that for the oxygen. And so as you go to bigger I, they get much, much bigger because actually the electrons are getting closer to the nucleus and less shielding. It's also kind of interesting. The ones in red here are the ionization to remove electron from the 1s orbital. And so notice that those dramatically increase as you have more protons into the nucleus because you have a stronger electrostatic attraction. The ones in blue correspond to removing the electron from a 2s orbital. And again, notice that they increase as you go to more protons. And the ones in green correspond to remove an electron in a 2p. And so it takes a lot more energy to remove a 1s electron from 1s than from a 2s than from a 3p. And the 1s is closer to the nucleus, so stronger electrostatic interaction, higher the ionization energy. So you should make sure that you understand this table and understand what those numbers correspond to. Another way of representing those numbers, again, I1 first electron, I2 second electron. And so lithium is an alkaline metal. It's in that first column. And so alkaline metals tend to form +1 ions because removing 2 electrons takes too much energy. Beryllium's in the second column, it's an alkaline earth. And beryllium, alkaline earth typically form +2 ions because removing 3 takes way too much energy. Boron aluminum typically form +3 because removing 4 electrons takes way too much energy. You're going down to a lower shell. And so again, this is the same for sodium, magnesium, aluminum. Sodium is alkaline metal, typically forms +1. Magnesium is an alkaline earth, typically forms +2. And aluminum typically forms +3. And so here's a periodic table colored based on the first ionization energy. The darker the color, the higher the ionization energy. The first ionization energy is given below the symbol. And so you notice as you go up to the right, first ionization energies increase. You can find exceptions, again, looking at the nitrogen, looking at the hydrogen. But in general, as you go up to the right, electrostatic interaction between outermost electron nucleus increase, the size decreases, and ionization energy increases. This is also consistent with metal elements versus non-metal elements. And so the elements in red are the metal elements. Their ionization energy is not as large, and so they tend to form positive ions. And here's the charge of the common ions. And so again, for that first row, they tend to form +1 ions, losing 1 electron. For the second row, they tend to form +2 ions. And so we've talked about the strength of electrostatic interaction between outer electrons and nucleus, the size, ionization energy. Electron affinity is the energy released when an atom or ion gains an electron. And so larger electron affinity, the more energy that was actually released. Now, if you have a negative electron affinity, that means energy was absorbed. And so if energy is released, you're going from something less stable to something more stable, releasing energy. And so with ionization energy, they're always positive. Electron affinities can be positive or negative.
Electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For example, when an electron is added to a neutral gaseous chlorine atom, 349 kilojoules per mole is released. In the case of chlorine and the other halogen elements, addition of an electron to the neutral atom is an exothermic process. Addition of an electron to the neutral oxygen atom is also an exothermic process. However, addition of a second electron to form the oxide ion is an endothermic process. This means that work must be done to force an electron onto the singly charged ion to form the oxide ion, O2-.
And so this means is that O2- will not form unless there's an attraction that makes it more stable, like if you have an ion-ion interaction. And so here's a table of electron affinities. Non-metal elements tend to have large electron affinities, and so they want to gain electrons. Again, you'll see notice that nitrogen is an exception to this because its half-filled subshell is extra stable. Most electron affinities in noble gases cannot be determined because they tend not to gain electrons. If an alkali metal gains electrons, they fill their outer s orbital, and so they actually have positive electron affinities. Nonmetals tend to have larger electron affinities than metals. Again, nonmetals tend to want to gain electrons. Metals tend to want to lose electrons. And so as we go up and to the right, electron affinity increases. The desire for the electrons increase. Now it's kind of interesting. This periodic table is colored based on electron affinities. You notice that the biggest trend is going from left to right and not necessarily going up, right? The fluorines really want to gain electrons. They have largest electron affinities. But in general, as you go up and to the right, electron affinity increases. And so we've seen as we go up and right, periodic table, the electrostatic interaction between electrons and nucleus increases, the size decreases, ionization energy increases, electron affinity increases. And again, this is consistent with metals versus nonmetal elements. The nonmetals are in blue, and they tend to want to gain electrons. They have positive electron affinities. Fluorine, typically, or the halogens that column to fluorine tend to form -1 ions. The chalcogens often form -2 ions. And so as you go up into the right, ionization energy increases, electron affinity increases, and the size decreases. Now, electronegativity is the measurability of an atom in a molecule to attract electrons to itself. The greater an atom's electronegativity, the greater the atom's ability to attract electrons to itself. And this concept was proposed by Linus Pauling.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end.
And so they really shouldn't show electrons as dots. Remember, electrons have wave-like properties, and so it's best probably to think about them in terms of electron density. But difference in electronegativity is very important because it enables us to determine which type of bonds are covalent, equal sharing of electrons, which ones are ionic, where you have a transfer of electrons, and which ones are unequal sharing, polar covalent. And so if the difference in electronegativity between two atoms is less than 0.5, we think about equal sharing. If it's greater than 2, we think about them being ionic, so there's a transfer of electrons. And if the difference in electronegativity is between 0.5 and 2, then we think about unequal sharing. And so this periodic table is actually colored based on electronegativity. And so we notice that fluorine is 3.98, basically 4. Francium is 0.7. Fluorine is the most electronegative element. And so all these are consistent. As you go up and to the right, the strength electrostatic interaction between the other electrons and the nucleus increases. And so the size decreases, the ionization energy increases, electron affinity increases, and electronegativity increases. And so again, that's consistent with the periodic table. And so these trends help us understand how these elements behave. You know, fluorine is going to be small. It wants to grab electrons, typically forms minus ions. I hope that was helpful.